coin change problem. And what it means is that we are given some coins like V1, V2, V3 till Vn. Okay, so we are given n coins, and so that all coins, all denominations, we can have change for all values, I make V1 is equal to 1. Okay, so now what happens, the problem is, if we are given a sum that is, let's say P. So I am given a sum P and I have to find out the minimum number of coins using which I can make the change. Okay, so let's say for example, so I have something like, I have some coins. So I have coins 1, 2 and 3. And now what happens, I want to make change for 5, the sum 5. So I can have 1, 1, 1, 1, 1. So this is one possible way of making change for 5. Other one is 1, 1, 3. Then we can have 2, 2, 1. Other possibility is 3, 2. So we see that minimum number of coins can be made using 3, 2. So I need 2 coins. So this is the problem here. We are given some coins which are V1 less than V2 less than V3 till Vn, and I'm given a sum amount S, and I have to make change using minimum number of coins, and this is called the coin change problem. Okay, so how to solve this problem? And we will use dynamic programming to solve this problem. So how to do? So using dynamic programming, we know that, okay, so if we have, let's say, let's represent C of P, which means this is the number of coins that is required, minimum number of coins that is required to make change for amount P. So now I have to solve this problem using dynamic programming, and it follows two principles. One is optimal substructure. Okay, so first one is optimal substructure. So what it means, so if I'm finding solution for a value P, and if I try to solve this using some sub problems, then all the sub problems that we solve, so their solutions should be optimal, and then we combine all the optimal solutions for sub problems, I should get a optimal solution for the main problem. And then other thing is that it should be overlapping sub problems. So another one is overlapping sub problem. So let's see what it means. So we start here CP, so that is the number of coins, minimum number of coins. This is the minimum number of coins required to make change for amount P. Okay, so CP is the minimum number of coins required to make change for amount P. Then what happens? Now we have to write our problem recursively, that is using solutions for smaller values. Can I solve CP, the problem of bigger values? So let's see. So I am given coins that are of denominations V1 is equal to 1, V2, V3, V4 till Vn. Okay, so these are the changes that we have, and I can use any amount of all of them. So what happens is I have to write some recursive relation between Cp and some value less than P so that we can solve the problem. So how to solve this? So first thing is optimal subproblem, and then overlapping subproblem, which is basically recursion. So can we write some recursive solution? So we have coins, only coins that we can use are v1, v2, v3 till vn. Okay, so what I do is I say let's Cp is the minimum number of coins that is required. So we will be coming to that value. This is equal to C of, okay, so we write this is equal to C of P minus V of I, and minimum for all I, this plus 1. So this is the sweet small solution. This is the recursive solution that we can write. And now you have to see how beautiful is this solution. So what I write is C of P, that is minimum number of coins required to make change for P, is equal to minimum for all I, that I have the coins v1, v2, v3. So I is from 1 to n, so I can choose any of these coins. So I say that minimum C of P minus Vi. So if I'm using last coin is minus v3, then it means I'm using 1 v3, and then I have to have optimal change of C of P minus Vi. So it means what? It is actually, if we enlarge it, this formula, so it will be something like minimum for all I and C of P minus V1, C of P minus V2, C of P minus V3 till C of P minus V of n. Okay, plus 1. This means what? I'm recursively solving this problem, and I say that okay, let us, and I'm using now, this is the optimal substructure. So what it says, I can come to Cp, so I have to make change, and what happens, that change I can make. So let's say that the last coin was, I can choose any one of the coins like v1, v2, v3. So if I use v1, that means I have now P minus v1, I should have the change already for that. And when I'm using Cp minus v1, this tells me this is the optimal solution I already know for P minus v1. So this is the number or minimum number of coins required for P minus v1 sum. C of P minus v2 means this is the minimum number of coins required when the amount is P minus v2, and similarly all. So what happens, now I say that I can use any of v1, v2, v3 till vn, and I subtract that amount and say that okay, the optimal solution for this will be the, I will choose the minimum among all the other optimal solutions for sub problems, and then because I am adding one more coin here, so I add 1. So this is the powerful recursive equation, and it follows both optimal substructure and overlapping subproblem. So basically, so this is recursive solution, and we are assuming that okay, C of P, so when I have already got optimal solutions for smaller problems or sub problems, and I'm using them to find the solution of bigger problem. So let's see this thing with one example. Okay, so I will take one example, which is I have coins, so V1 is 1, V2 is 2, V3 is equal to 3. Okay, so I have 3 coins, and let's say I want to make a sum which is 5. So I have to make a sum which is 5. So in how many ways I can make, and what is the minimum among them? So what I can do is, let's try to first solve it. We had already solved this, and I know 3, 2 is the best possible way. So 2 coins I need for making change of 5. So how we do it? With dynamic programming using this recursive equation. So I know that, okay, so C of P is equal to minimum among all I, and it will be C of P minus Vi plus 1. Okay, so this was the thing. So now I come and I say that, okay, C of 1 will be what? So this is, I have 1 coin and 1 minus, so it will be minimum for all I, and C of 1. So first one, if I use it, will be 1 minus 1, and others I cannot use. So okay, so this will be plus 1. So this will be basically, we know it is 1. So for making a change for 1, I have to use 1 coin. So now to make a change for 2, what will I do? I will have min I and then C of, so first is 2, so I can use 1 as a change. I can use 2 as a change, but I cannot use 3 because it is going below 7. So here you can put one more restriction, that okay, I which I am choosing, so that Vi should be less than P. Okay, so these are the 2 things I can choose, plus 1. So now I get, so this is minimum of C of 1, which was 1, and this is C of 0, which is 0, plus 1, so which means 1. So this is 0 plus 1, which is 1. So yes, so this is true also. I can make a change for 2 using just 1 coin. So similarly for C3, so this is minimum of, for all I, so all coins I use C of 3 minus 1, then C of 3 minus 2, and C of 3 minus 3, and plus 1. So what happens now is, this is minimum of C of 2, comma C of 1, comma C of 0, plus 1. So C of 2 was, we saw 1, this C of 1 is also 1, and C of 0, if you have no some amounts, and this is 0. So minimum of this plus 1. So again minimum of this is 0, so this is 0 plus 1, 1. So that also looks true to us. Now let's see how can we make amount 4, change for 4. So C4 will be minimum C of 4 minus 1. So whatever coins I can use, C of 4 minus 2, C of 4 minus 3. These are the only possible coins, plus 1. So this means what? I have changed best possible changes for 1, C1, which is 1, C2 is also 1, and so this is C3. Basically I can have change using just 1 coin, C2 also 1 coin, and for 1 also I can have 1 coin and plus 1. So this comes out to be 2. So 4 I can make using, in minimum number of coins is 2, and we see here that okay, 3, 1 we can use, 2, 2 we can use, but we cannot get minimum than this, lesser than this. 1, 1, 1, 1 will make it 4. So C4 is also okay. So now we will look for C of 5. So C of 5 will be minimum I. So it will be C of 5 minus first value if I use C of 5 minus 2, C of 5 minus 3. So these are all the possibilities of using the coins, and plus 1, so whichever we used. So now C of 4, C of 3, C of 2, these are the possible cases. So minimum of I plus 1. So C4, now we have to use C recursively back. So I already know the optimal solution, that okay, to make a change of 4 I need 2 coins minimum. So I will write here 2, for 3 it was 1, for 2 it was 1 coin, plus 1. So what happens? So this is minimum among them is 1 plus 1, so this is 2. So C of 5 we can make using 2 coins, so which will be clear also. 5 I can make with 3 plus 2. Okay, so similarly 6, how many coins? We can again do it with 3 comma 3, and we will just try out for 6 also. Okay, so C of 6 will be equal to minimum of, for all i's, so C of 6 minus 1, C of 6 minus 2, C of 6 minus 3. So this makes what? 5, minimum of C of 5, C of 4 comma C of 3 plus 1. So we see that C of 5 was 2, C of 4 was also 2, and C of 3 was 1. So minimum of this, so it will be 1 plus 1, 2, and we see that 6 can be made equal to 3 comma 3. So this was what is dynamic programming, and let's see how it happens. So what we did was, 2 things we have to keep in mind while doing dynamic programming. First thing is that we divide the problem into smaller problems called sub problems, and then we try to solve the sub problems which are easier. So we go from bottom up, and we say that okay, so the smaller problem, because we are using them, so we say that we should prove that okay, if we combine the solutions for optimal solutions for smaller problems, and they should combine to make the optimal solution for the bigger problem. So this is one criteria, and another is overlapping sub problem. So basically recursion, we should be able to present the problem as relation with the smaller sub problems. So we should have some recursive equation. So here what we did, if we wanted to have minimum number of coins for amount P, that we can obtain using what we can have. So last coin, let's say this is basically choosing the last coin. So we say that okay, if I have to calculate P, and I have say that okay, minimum number of coins required was, let's say M, some M. So basically I already know for M minus 1 what is the minimum number of coins. So basically in the last coin that I can choose is, it can be V1, it can be V2, it can be V3, or it can be Vn, anything. So what I say that whichever I choose, and each one of them will have optimal value, like each will have a C of P minus V1 will have some, it will be minimum number of coins required for P minus V1. So we find the minimum among them all, and because last coin we are using, so we add 1 to it. So this gives us the solution. So if we solve this, like we have V1 is equal to 1, so 3 coins we had, and we had to make amount of 5 or 6. So we started, so with 1 rupee or $1 we can make using just 1 coin. $2 we can make using just 1 coin. I can use this one. $3 similarly I can make using 1 coin, even though I could have used 2 coins, 1 comma 2, but minimum is like 1 coin. So 4 I could have made in minimum number of coins. How? So one thing is that I know that okay, I have 3 coins For rupees 3 or $3, I already know the minimum number of coins. Then I can say that okay, I choose $1 coin and add it to it. I can have optimal solution for amount 2, and then I can add our coin with denomination 2. We can have optimal solution for amount 1 and then use the $3 coin. Okay, so this is how we proceeded, and we solved the dynamic programming to have minimum number of coins required to have a change for some amount P. So I hope you understand this, and if you like this video, please share it with among your friends and subscribe to my channel. Thanks a lot.